In the aviation industry, there are tons of planes flying in all sorts of directions with lots of people at different speeds and different altitudes that it becomes imperative that they all communicate with the same frame of reference. That frame of reference is the compass rose. Now, we are looking here at a navigational chart of the Denver International Airport airspace. And what you see, the yellow here is Denver, and here is Denver International Airport. You can see all the runways. You can see that this compass rose is always identified with 0 degrees acting north. So it is this frame of reference that all pilots agree upon, because if they don't, that is where safety issues come into play. Well, as you look at this map, you can see a couple things. First of all, the concentric circles around Denver International Airport, or DIA, represent different altitudes. So planes have to be at different altitudes the closer they get to the airport, and that defines their airspace. Let's show the resultant in both of these ways using our example of me getting from my house to Jim's house. Let's do a little bit of erasing over here, and let's begin with component form. Component form is probably the easiest way because it's read it right off the picture. I can see that in my example I have defined or oriented my I and J axis such that from this picture point of view I can see that I walk 5 houses in the positive direction. Now, because I'm on the picture and my arrow is on the y-axis, I don't need to put I right here because I'm on this axis. And right here I can see once I'm at this point I walk up 2 houses. And we take this information and we use that to communicate our resultant. Now, the resultant in this case is a vector form, so I would write 5 houses in the I direction and 2 houses in the J direction. And so this form right here is component form. Now, we already showed that one. Let's go back to the magnitude of polar form. Well, I've been given these 2 pieces, and so I know that on this picture, this side right here is 5, my adjacent side is 5, and my opposite side is 2. So running them into and using the Pythagorean theorem, I am able to determine the magnitude, which is the square root of 5 houses plus the squared plus 2 houses squared, and my magnitude comes out to be 5.39 houses. So I could say that Jim is 5.3 houses away from me. Well, that doesn't make a whole lot of sense because, you know, how big's a house, number 1, and number 2, in which direction is Jim? So this shows purely the magnitude that I would have to walk, but in which direction? Now, the direction comes from using this relationship derived from trigonometry and the definition of the tangent. Well, my angle is defined as taking the inverse tangent of the opposite side. Well, we define theta to be here, so the opposite side would be 2 houses divided by the adjacent side, which is 5 houses. You see, houses go away, and we are left with units of, with no units, but as we define an angle, this arrives at the units of degrees. And so by taking the inverse tangent of these values, 2 divided by 5, and taking the inverse tangent of that, I get 21.8 degrees. This is one of those things you'll want to make sure that your calculator is in degrees on. Okay, I understand that I'm a bit weak right here in communicating why this comes out. House divided by house is a house divided by house is a unitless value, so where's this degree come from? This understanding really comes from a deeper understanding of trigonometry, but the ultimate relationship comes from an understanding of what's called the unit circle and how far around that circle you are. So, and degrees is a measure of how far you are around that circle. So I don't want to say any more than that, but you want to make sure that your calculators are in degrees when you do numbers like these. Any number. For this course, you will be using degrees, and there will be one part in circular motion when we'll get a little bit more information on the tangent, understanding of this circle thing, where another unit is measured in radians. So hold those thoughts. For now, you've got enough information to understand how this process works based on the definition of this relationship. Now we say 21.8 degrees. From where? Well, this is where. This is where, knowing the I, J, K axis as being confident with it and the fact that it shows direction, in addition to the terminology of what a component vector is and how we defined theta, that this side is adjacent to theta, this side is opposite theta. These are both components, therefore perpendicular, which makes our relationships of cosine, sine, and tangent true. We defined theta, I-axis, I-J-axis. We defined theta to be here. Now, if you don't draw an accurate picture, you won't know where that theta goes. But we defined theta to be here. And so, 21.8 degrees will be measured from this point up to your resultant, period. Okay, so we have seen an example of how to communicate, if you've got both components, how to determine the magnitude and the direction of this resultant in both component form and polar form. Okay, what if you don't have the components? What if you are given the resultant? This whole discussion has been from the point of view that you knew what these two components were. What if, in fact, you didn't know these, but you did know what the resultant was? Well, we have to then take our process and reverse it. We'll talk about that next.